Hey everybody. Today we're going to talk about rational and irrational numbers. And these are two very important groups of numbers, and it's important that we distinguish between the two. So this lesson starts off with some important vocabulary words, some of which you have seen before. So we're going to go through each of those. Let me do it like this. So the first is real numbers. So real numbers are defined as the set of rational and irrational numbers, and we'll get to what each of those means in a minute. Natural numbers are known as your set of counting numbers. For example, and I want you to write this in, the counting numbers. When you first learned how to count, what's the first number you started off saying? 1, 2, 3, 4, and so on. So that's your natural numbers, also referred to as counting numbers. Now, whole numbers are your natural numbers, the ones we just talked about, plus 0. So a number, all natural numbers, are also considered whole numbers. Now, here's the next part. Integers, it gets a little bit confusing. An integer is just the set of whole numbers and their opposites. Just because a number has a negative in front of it doesn't make it an integer. So negative 4.8, not an integer. An integer doesn't have that decimal portion attached to it. Now, the counting numbers we just discussed, they are integers also. Okay? Rational number. Now, here's what we really want to talk about. A rational number is any number that we can write as a ratio of two integers. In other words, we can write it as a fraction. So let's write that down. Can be written as a fraction. Now, all fractions become either repeating decimals, remember that bar notation, or terminating decimals. A terminating decimal is a decimal that does not repeat. It just ends, okay? So all rational numbers are numbers that can be written as fractions, and all fractions end up being repeating or terminating decimals. An irrational number is any number that we cannot write as a fraction. And since we cannot write it as a fraction in decimal form, those are your non-terminating, non-repeating decimals, meaning they go on forever without any type of repetition. Okay? Your very most famous irrational number, guys, is pi. Pi is the most famous irrational number. Now, your teacher in the past may have told you to use 3.14 for pi. The reason your teacher told you that is because 3.14 is an estimation of pi. Pi is really an irrational number that goes on forever without repetition. Just try typing pi into your calculator, like the pi symbol, and hit enter. It's a really long decimal number. Now, your calculator doesn't show you all the decimal places for pi or other irrational numbers. How could it? Irrational numbers go on forever without repeating. If every time we use the pi key in our calculator, then the calculator's broken because it would be forever, okay, doing the next digit, next digit, next digit, next digit, and so on in pi. So pi is an estimation we use for is 3.14. On your calculator, it takes it out to 7, 8, maybe 9 decimal places, but it's still, that itself is still just an estimation. The calculator has to cut it off at some point, so that way we can work with it. Okay, moving on. So then they talk about square root, which we already know what a square root is, and the radical symbol. Now notice here when they did the radical symbol, they've got 2. Remember that we've got that cubed root symbol, right? The little 3 means the cubed root. So if you see just this, technically you're being asked to find the positive square root. If you see the negative sign in front of it, then they want you to give the negative square root. And if you see that plus minus in front of the radical symbol, then you're asked to find both square roots. And then it talks about what is a perfect square, which we've already defined. Okay, so then it says list of first 15 perfect squares. So why don't you go ahead now and pause the video and list out the first 15 perfect squares and then come back. Great, guys. All right, take just a couple seconds and make sure that you have the first 15 perfect squares listed correctly on your paper. Great. All right, so let's look at the next part. It says provide 2 examples that show that the statement is false. Lydia said that all square roots are irrational numbers. Now, let's go back. What is an irrational number? An irrational number is a number that cannot be written as a ratio of 2 integers, meaning that they are non-repeating and non-terminating decimals. Okay, so we want to prove what Lydia said was false. She says all square roots are irrational. Well, we could say, what about the square root of 4? That is not irrational because the square root of 4 is 2. 2 is a terminating decimal. It ended. It's the same as 2.0. So that's false. We could also say the square root of, say, 169. That's equal to 13. So all square roots are not irrational numbers. However, if I'm taking the square root of a number that is not a perfect square, then it will be irrational because it will be that non-terminating, non-repeating decimal. So I'm going to say that again. Every time you're taking the square root of a number that is not a perfect square, it will be irrational every time. Okay, so let's go to the next page. It says to classify the numbers as rational or irrational. So the square root of 77. Is 77 a perfect square? No. So then its square root is going to be irrational. What about the square root of 48? Well, is 48 a perfect square? So its square root is also irrational. So it says explain why number 3 is rational or irrational. So number 3 is irrational. So I'm going to say the square root of 48 is irrational because 48 is not a perfect square. When we take the square roots of perfect squares, we end up with whole numbers or integer values. Okay, let's go to the next part. It says find the square roots for each number. So number 5, the square root of 121. So that's what it's asking us to find, the square root of 121. Well, that would be 11, right? Plus positive and negative 11. Remember, each number has 2 square roots, a positive and a negative. What about the square root of 81? So that's going to be positive and negative 9. Okay, and then number 7 says explain why number 6, and I think we're supposed to say is rational or irrational. So the square root of 81, is it rational or irrational? It's rational. The square root of 81 is rational because 81 is a perfect square. Now, the other numbers can be written we can look at other numbers that are not written with the radical sign, like decimal numbers, for example, and classify them as rational or irrational, okay, as well. But they're a little bit easier to tell. For example, number 8 is negative 8.875. So it's a decimal, right? Is it a terminating or repeating decimal? Well, it's not repeating. Does it end? Yes, this one ends. So therefore, it is rational. Okay? What about the square root of 16? So anytime you're looking at square roots, and you want to determine rational or irrational, look and see the number underneath the square root symbol. Is it a perfect square? Well, this one is. Remember that the square root of 16 is 4, positive and negative 4. So this is also rational. What about number 10? Okay, so this is a decimal. Do you see the dot, dot, dot right here? This indicates that it goes on, it continues on. So it does not end. But just because it doesn't end doesn't mean that it's automatically irrational. It has to go on forever and not repeat. Now, does this repeat? Do you see any repetition pattern in that decimal? I don't. So this is a non-terminating, non-repeating decimal. So yes, this one is irrational. Okay? All right, so now what I'm going to have you do is I want you to do 11, 12, 13, 14, 15, and 16. So I want you to go now, I want you to pause the video and do 11 through 16, and then we'll come back and check. Hey everybody, welcome back. So I want you to pause this video so that you can check over your answers for problems 11 through 16. Make sure that you showed your work. Go ahead and do that now. Great. So number 11, I had to just provide 2 examples. Your examples may not have been the same as mine. For 15, again, your example in number 15 may not have been the same as mine. For problem 16, however, you should have shown work, okay, and you should have the same answer. They would not be the same value. Okay, if you've got any questions about the work from today, please bring those to my attention so that I can assist you. Okay, go ahead and turn this in and then work on your independent practice.